A microservice crashed with OOM-killed every 15 minutes under moderate load. The team assumed a memory leak, but the real culprit was SERIALIZABLE isolation, causing transaction retries to pile up MVCC snapshots until the 4 GB container limit was breached. Let's break down why ACID isolation levels can be dangerous and how to fix it. Welcome to TheCodeForge. Before we dig into that production issue, let's cover ACID versus base. ACID stands for atomicity, consistency, isolation, durability. Think of it like a bank vault. Every deposit and withdrawal is recorded instantly and exactly once. If the power goes out mid-transaction, the vault locks and nothing is lost. Base stands for basically available, soft state, eventual consistency. It's like a whiteboard in a busy office. Someone writes a number, someone else erases it, and eventually everyone agrees on the final count. It's fast and works even if people are in different rooms, but you might see the wrong number for a moment. Here's a classic ACID transaction. Transferring $100 from account A to B. If the server crashes between the two updates, the transaction is rolled back. Atomicity ensures both happen or neither. This SQL shows a simple transfer. The begin and commit wrap the two updates. If the system fails after the first update, the database rolls back the entire transaction, leaving the accounts consistent. In Cassandra, a write with consistency one succeeds as soon as one replica acknowledges, but subsequent reads may hit a different replica that hasn't received the update yet, returning stale data. For critical paths, use quorum consistency. This CQL inserts a like with consistency 1. It's fast but eventual. If you need strong consistency, use quorum for both reads and writes. Optimistic locking avoids locks by using a version column. You read the version, compute the update, and then update only if the version hasn't changed. If it has, you retry the transaction. This is great for high concurrency scenarios. This SQL uses a version column to implement optimistic locking. The update only succeeds if the version matches. If another transaction changed the row, the update affects 0 rows and you retry. In DynamoDB, to ensure read-after-write consistency, use consistent read equals true on getItem. This guarantees you see the latest write, but it consumes twice the read capacity units and has higher latency. This JavaScript shows a write followed by a consistent read. The consistent read equals true parameter ensures the read returns the latest data. Use this for critical paths like session management. Many systems use both, an ACID database for transactional data and a base store for read-heavy workloads. For example, write orders to PostgreSQL, then asynchronously update Elasticsearch for search. The search may be slightly stale, but that's acceptable. This code shows the hybrid pattern. First write to PostgreSQL with a transaction, then asynchronously update Elasticsearch. The search index may be stale, but the order is safe. This is the same issue we highlighted at the start. Here's exactly why that happened. The service used SERIALIZABLE isolation. Under concurrency, transactions retried exponentially, each retry holding a snapshot of the entire database in memory. The 4 GB container limit was hit because each retry accumulated more MVCC snapshots. The fix was to change isolation to read committed and add retry logic with jitter. Also increased container memory to 8 GB as a buffer. This resolved the OOM issue and prevented recurrence. Always benchmark your transaction, retry memory footprint under peak concurrency. SERIALIZABLE isolation is not free, it trades memory for correctness. The production incident we opened with. A 4 GB container kept dying because SERIALIZABLE isolation caused retries to accumulate MVCC snapshots in memory. The fix was to use read committed and add retry jitter. A common mistake is using SERIALIZABLE isolation for all transactions. This adds heavy locking and can cause retry storms under concurrency, leading to OOM crashes. Use the weakest isolation level that guarantees correctness. If you write with 1 and read with 1, you may get stale data because the read hits a different replica. Always match read and write consistency levels for critical paths. Don't assume eventual consistency means within milliseconds. In a partitioned network, it can take minutes. Always set a TTL or timeout on reads to avoid serving data that's too stale. ACID's durability guarantee depends on the database actually flushing writes to disk. If the file system or disk controller has write-back caching enabled common on cloud instances, a power failure can still lose committed transactions. Always verify that your database is configured to issue fsync and that disk caches are in write-through mode. For PostgreSQL, check synchronous commit and full page writes settings. The article mentions read-after-write consistency, but doesn't show how to achieve it in Cassandra. Using consistency local quorum for both writes and reads, and optionally use the CL option in the driver to force the read to hit the same replica that handled the write. Below is a Java snippet using the data stacks driver. The article covers stale reads in Cassandra, but not in DynamoDB global tables. When using multi-region replication, writes are eventually consistent across regions. A read in one region may not see a write from another region for up to a second. This can cause issues for user sessions that span regions. Mitigation: use DynamoDB's consistent read only in the same region as the write, or use a global secondary index with strong consistency disabled. To debug deadlocks and retry storms, first check block transactions with PG locks, then cancel the blocking queries. Ensure all transactions access tables in the same order to prevent deadlocks. Consider lowering isolation level to read committed. Let's run through some common interview questions. How does PostgreSQL handle SERIALIZABLE isolation? Uses SSI with predicate locks, aborts on conflict. When to choose DynamoDB over PostgreSQL? For single-digit MS latency, eventual consistency, no complex queries. How to handle read-after-write in DynamoDB? Use consistent read equals true on getItem. And a few frequently asked questions. What is the main difference between ACID and base? ACID guarantees strong consistency. Base prioritizes availability. When should I use ACID versus base? ACID for financial transactions, base for social media feeds. Can a database be both ACID and base? No, but you can use a hybrid architecture. Key takeaways: ACID is not always safer. SERIALIZABLE isolation can cause retry storms. Base does not mean no consistency. You must handle stale reads. Use ACID for the source of truth and base for read-optimized caches, and always verify your durability settings. Ready to go deeper? Up next, change data capture CDC, then database federation, then NoSQL store types compared. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.